Hello, I'm Roger Fawcett, Managing Director of Omnitek, and I'm going to tell you about the advanced physical layer of the Ultra 4K toolbox. So the advanced physical layer builds upon the standard physical layer in the 4K toolbox, which gives you eye pattern and jitter meters up to 6 GHz. The advanced physical layer extends this eye pattern to 12 GHz and also adds a jitter spectrum, jitter waveform and jitter histogram on the analysis side. On the generation side, it enables you to insert jitter onto your signal of a controlled amplitude and frequency, and it also enables you to adjust the output voltage and output slew rate. So these are a very comprehensive set of tools that go well beyond traditional video products and give you the sort of analysis that you would normally only find on a high-end oscilloscope like this one here, which costs many hundreds of thousands of dollars potentially. So I'll now go through each of these features in turn to explain a bit more about them. I'm starting with the eye diagram. So you can see here that we have a very nice 12 gigahertz eye pattern, and on the oscilloscope here I also have the same signal captured as a moment ago, and what you can see straight away is that we have a very clean high frequency response eye diagram which gives very similar figures. So for example, if you look at the rise time, you can see that we're measuring around 34-35 picoseconds and an amplitude of about 750 millivolts on this particular signal, and again on the oscilloscope here we see almost identical figures. So to demonstrate further the consistency of the eye pattern reading, I've now got a 10 meter cable plugged into the Ultra and captured the same signal on the oscilloscope, and once again I can now see my rise and fall time has degraded on the Ultra to around 41 picoseconds, and equally my amplitude has degraded to about 520 millivolts, and I see the same readings on the scope here. So I'm now going to show you two of the generator features of the advanced physical layer, and these are the ability to adjust the output voltage and the output slew rate, and I'll use those to demonstrate the real-time nature of the eye diagram. So at the moment the eye diagram I have set up has got a large persistence on it, so it gives a very smooth, accurate eye diagram. But if I slow down the persistence, I'll get a slightly more grainy eye diagram that will have a more responsive real-time update. So I'll do that now. And now what I'll do is I'll show you the voltage control. You can see that changes instantly. So I can adjust that to a range of values to suit whatever I want to test. So I can also adjust the slew rate. Now for 12 GHz in particular, normally you'd want the fastest slew rate possible because you want a fast rise time to give as much energy to the high frequencies. However, to test receiver tolerance, you may well want to try a slower slew rate to see how much headroom there is. So I can adjust this now, and once again you can see my eye diagram has closed up quite considerably, and I've got a poor eye diagram, but I'm still hanging on to the STI signal. And also you'll notice the instant response of the eye diagram, and again if I change this back, you'll see that changes back again instantly on the eye diagram. Okay, so I'll now show you the jitter histogram, the jitter spectrum and the jitter waveform, and I'll use the jitter inserter capability to demonstrate these. So first of all, to look at the individual tools, so the jitter spectrum is shown here, and it shows a Fourier transform of the jitter waveform in effect, and it goes right up to around 22 megahertz frequency, and in fact higher frequencies can also be seen on the eye diagrams. That gives a very wide range of jitter tracking. And this tool enables you to pinpoint very specific things. It might be a power supply, it might be beating between clocks, but it enables you to pinpoint the exact frequency and therefore likely the source of jitter. The jitter histogram shows the probability density function of the jitter perturbation as a function of frequency. And finally, the jitter waveform just shows the jitter plotted against time. One thing to note on the jitter spectrum is that it automatically finds the top peaks. You can find up to the top 20 peaks. And it will give you a list in order of magnitude, so you can instantly see at the top which are your worst offenders when you're trying to get a low jitter output. So now I've turned on the jitter insertion, and I've chosen to put 20 kilohertz of jitter at 2 UI onto my signal. And then if I look at the displays now, I can see My jitter spectrum here shows me a peak at exactly 20 kilohertz of the right amplitude, so it's picked that out in the frequency. I can see on my histogram here a classic dual Dirac distribution, which is the sort of thing you expect when you've got deterministic jitter. And also on my jitter waveform, I can see the sine wave that I've been inserting on the jitter. And whilst I'm doing this, I've also got the status window here, and I'm monitoring CRC errors, and I can see that that I'm not getting any CRC errors due to this jitter insertion. So to wrap up, the Advanced Physical Air package contains a lot of tools for both analysis and generation to enable design engineers and system installation engineers to debug and design 6 and 12 gigahertz systems. And these go well beyond traditional waveform monitors. And so on the analysis side, again, we have 12 gigahertz I pattern, jitter meters, jitter spectrum, jitter histogram, and jitter waveform. And then on the generation side, we have output jitter insertion, output voltage control, and output slew rate control.